we learned when we were finding the arc length in R2 or 2 dimensions. We found R2 in its parametric formula. So what we essentially did was, given a curve on plane RT with its vector x of t and y of t for t from A to B, our change in our length or our change in the derivative of the curve is about the change in x divided by the change in t squared plus the change in x divided by the change in t squared times its change in t. If we found the limit as n approaches infinity, or as these dt's get infinitely smaller, we found that the arc length in parametric form will be equal to the definite integral of the square root of x dx over dt squared plus dy over dt squared with respect to t from A to B. So in R3, we're really just applying the parametric form with respect to t with z as our extra variable. So in R3, given a curve in space, RT, which equals the vector x of t, yt, and zt for a t that's between A and B, and our arc length formula will actually equal the definite integral of the square root of dx dt squared plus dy dt squared plus dz dt squared with respect to t from A to B. And really what this is the definite integral of the magnitude of the derivative of the curve RT with respect to t. So how we got that was that if we find the magnitude of the derivative of RT, we get what's inside this definite integral. Similarly, we can find the arc length of a polar curve. Given that we have a function r equals f theta for a theta between alpha and beta, our arc length equals the definite integral of the square root of f of theta squared plus the derivative of f of theta squared with respect to theta from alpha to beta. And we can also set arc length as a parameter. Given we have the curve RT with the vector xt, yt, and zt, we actually just set the curve as a reference to t equals a in the positive or negative direction. We find that the arc length function, it equals to st equals to the definite integral of the square root of the derivative of x of u squared plus the derivative of y of u squared plus the derivative of z of u squared with respect to u from A to t. By using a arc length as a parameter, it can be very helpful for us when trying to calculate the curvature. Today I'll be showing you this arc length example in R3. Okay, given that we have a RT which equals the vector in its I, k, and j form equals 4 sine t I plus 3tj plus 4 cosine t k from 0 to 2 pi. We first want to write out our arc length formula, which equals the definite integral of the square root of the derivative of t squared plus the derivative of g of t squared and the derivative of h of t squared with respect to t from A to B. And we also know that actually equals the magnitude of the derivative of RT as well. So we can first find the magnitude of the derivative of RT first. So when we try to find that, plug in the x component, y component, and z component and simplify, we get that the magnitude of the derivative of RT equals 5. And plugging that 5 into the original equation, we get that the arc length in R3 for this problem will be 10 pi. So try to do this question on your own and then check back with this answer later. I hope my video was helpful in your understanding on how to calculate the arc length in R3. Thanks for watching.